All right, here we go. It's lesson 11.7. Here's your homework. All right, today is going to be a lesson on areas. Well, that's what the whole chapter's on. And we're going to combine it with the term ratios. So it's going to be ratios of areas. All right, one theorem today. We're actually going to prove, we haven't proven a theorem in a while. All right, so ratios. What's a ratio? Well, a ratio is a comparison of two values, so two numbers using division. Generally speaking, we write this in fraction form. Remember, fraction bar means division, so that's A compared to B using the division symbol. You can also use the colon form as well too, or you could use the words A to B, A T O B. Those are the three ways to write a ratio. So today we're going to be doing ratios, but the two numbers, the A and B, are going to actually be areas. So we're going to compare two areas and form a ratio. We're going to do three basic constructions here. So imagine this. If I take a triangle and I label the height, so that red dotted line is the height of that triangle, and then I make another line, not a height, but I'm going to split the triangle up into two more triangles. So we've got the triangle on the left, and we got the triangle on the right there. All right, so I've broken this triangle into two triangles, three if you count the larger triangle. And then I'll make it all fancy with letters and values here. So let's see. This is the larger triangle ABC, which is broken up into two smaller triangles, the green triangle and the orange triangle. And it appears that both of those triangles have the same height. So if I were to compare the areas of the green to the orange triangle and write a ratio of that, well, let's see what would happen. So I need the areas of the green. Remember, ratio is a fraction. So I'm going to write a ratio of the areas. And I'm going to compare green to red, or green to orange, sorry. So let's see. So I need area. So let's see. What's the area of the green triangle? Well, the base is A and the height is H. So AH divided by 2 would be the area of the green triangle. Let's see, the area of the orange triangle. Well, look, it's got the same height. The orange triangle has the same height as the green triangle. So therefore, let's see, the base of the orange would be B. So B times H divided by 2. And now I want to make a ratio of those two areas. And I just picked one. I could have done orange to green, but I chose green to orange. So let's see, green to orange. Well, green is a fraction and orange is a fraction. So I'm going to wind up with a fraction over a fraction, and that's my ratio of green to orange. AH over 2 divided by BH over 2. Now it looks a bit like a big hot mess, but remember, if we have let's see, if we have a fraction over another fraction, we can do a copy dot flip and get one fraction out of it. So let's see. The top one I'm going to leave alone. The bottom one I'm going to flip and multiply the two together. And check it out. There's a bunch of things that cancel there. Well, first and foremost, the 2's cancel. And the H's cancel. And so I'm just left with A over B, which is the ratio of the bases of the triangle. So let's see how we started this off. We started off by creating a ratio of the areas of the two triangle. And after we did a whole bunch of arranging and canceling, we wound up with the ratio of the bases. So what just happened? I asked you to create the ratio of the areas of two triangles and that had the same height. And you found out that that was actually the ratio of the two bases. All right. And that's what just happened. So if two triangles have the same height, well, then the ratio of their areas is equal to the ratio of their bases. All right, we will write this down, just not right now, because we're going to do another construction. All right, so now a different construction, still with triangles, though. All right, so there's a triangle. I'm not claiming it's a right, obtuse, acute, or anything like that. It's just a triangle. And this time I'm going to make a triangle inside the triangle. So I've got a big triangle on the outside, and inside I got a smaller triangle. But check it out. They both share the same, not the same heights. They clearly right there have different heights, but they do in fact share the same base. So here's the fancy one right here. So I've got a light blue triangle, that's the big one, and I've got a dark blue triangle, that's the small one. And I'm going to do the same trick. I'm going to ask you to write the ratio of their areas. So we're going to do light blue to dark blue. And now these two triangles share the same bases. They do not share the same heights. The previous one, they shared the heights. So let's see what happens to that ratio if they share the same basis. So same thing. So the blue triangle, the big one. Well, the base is B, the height is H, so BH over 2. And for the dark one, let's see, the base is B, the height is K this time, so BK over 2. And if I write the ratio of those two areas, I would get that. And then I'll do the same darn trick, copy dot flip. So I'll do a copy of the top fraction, BH over 2, times the bottom fraction flipped, and a whole bunch of things cancels. The 2's cancels, the B's cancel, and so I'm left with H over K. So if you have two triangles that share the same base, and I ask you to create the ratio of their areas, we find out it's actually the ratio of H and K are the heights of those two triangles. So what just happened? Two triangles share the same base. The ratio of their areas is equal to the ratio of their heights. So if the words seem a little jumbled together with you, let's put them all on one page. Quick pause on that. So what is the ratio of the areas of two triangles? Well, if they have the same height, well, then it's going to be the ratio of their bases. If they have the same base, then it's going to be a ratio of your heights. We haven't written any of this down, but we will in just a second. We've got one more construction to do. All right, so imagine this. We're not going to put a triangle in a triangle. This time we're going to make two similar triangles. So there are two similar triangles. And remember, we've already done a whole chapter on similar triangles. When two triangles are similar, that means that their angles corresponding the angles are congruent and their sides are in proportion. So for instance, I wrote the proportion H over K. So small triangle over big triangle is equal to B over E. All right. So what am I going to do? I'm going to do exactly the same thing. I'm going to ask you to write the ratio of the areas of small triangle to big triangle. All right, so let's see. The first triangle would be BH over 2, and the second triangle would be EK over 2. Same drill as before, and then do a copy dot flip. If I'm going too fast, pause, think, and then rewind. Now cancel. The 2's, well, that's the only thing that cancels is just the 2. So it looks or it appears I'm left with that, but it turns out I can do some magic here. So I need a new page to do the magic. So let's see, similar triangles, I wind up with BH over EK. All right, so if I have that fraction BH over EK, I could, let me draw this for you, I could split this fraction straight down the middle and just put a dot in between those two fractions. So B over E times H over K would be the same darn thing. All right, now let's think about this. We've seen both of those letters before, B over E and H over K, right? Well, if I rewrite B over E, right, all I did was I'm rewriting that multiplication there. So I start with the B over E, but this time I'm not going to write H over K. Why? Because remember, for similar triangles, you get that proportion right there. For these two similar triangles, you get that proportion over there, which is what we started with. H over K is equal to B over E. So I could do a substitution. What's the substitution? Well, I'm supposed to write times H over K, but this right here says if you see H over K, we can write B over E. So I'm not going to write H over K. I'm going to write B over E, right? So I'm going to substitute for that H over K, B over E. So let's do that substitution. Let me erase the mess I just made, and let's multiply straight across, and we get B squared over E squared. So we arrive at our final answer, or our final comparison of the ratio of the areas. Well, what is B squared over E squared? B squared over E squared are the bases squared, but those are also, I mean, easily stated as that's the scale factor. Remember, the scale factor of any two similar triangles is pick a side, any side, and write a ratio of its corresponding side. I could have written H over K, but I chose to write B over E. And remember, we've just figured out that this is not just B over E, it's B squared over E squared. So that's our final statement. Now we're ready to write this stuff down. So what just happened? If you have two similar triangles, and if I ask you to write the ratio of their areas, then the ratio of the areas is equal to the square of their scale factors. All right. Quick note for similar shapes, remember the scale factor is the ratio of any two corresponding parts. So even though I used B over E, I could have used H over K. All right, so we're going to write these down now. This is not the theorem. We'll get to the theorem here in a second. But remember we had three constructions, and these were all with triangles. Now we did prove these. These technically could be theorems. So the first one says, well, I'm gonna write them all out right here. So the yellow is the important part. The black is the explanation of this. So remember, if two triangles have the same heights, then the ratio of their areas is equal to the ratio of their bases. That's the first statement there. Second one is, well, if two triangles share the same bases, or have equal bases, then the ratio of their areas is equal to the ratio of their heights. And the last one is, if two triangles are similar, then the ratio of their areas is equal to the square of their scale factors. Remember, the scale factor is any two corresponding sides. All right, go ahead and pause the video, write that down, and when you're ready to go on, play. All right, so that is a lot of information. Boiled down simply, if you got the same heights, then the ratio of the areas is going to be the ratio of their bases. If you got the same bases, then the ratio of the areas is equal to the ratio of their heights. And lastly, if you got similar triangles, then the ratio of the areas is going to be the scale factor squared. That's it in a nutshell right there. All right, what do you do with this? Well, you're going to solve some ratio problems. What are they going to look like? Well, here's 3 problems. And these are some confusing problems. I will say, generally speaking, many students have some issues with some of these problems. I'll try to do this nice and slow and repeat rewind and repeat if you need any help. All right, so here's the 3 confusing problems using one picture. So the first one I'm going to give you, it says, what is the ratio of the areas of triangle COD to triangle AOB? Well, the first thing is just finding those 2 triangles. So let's see, COD is right there and AOB is right there. Remember, we have 3 possibilities. They either are going to have the same heights or the same bases or they're similar triangles. Of those 3, well, clearly just by visual observation, they don't have the same heights and they definitely don't have the same bases. Are they similar? Well, notice we were given with this arc, the angle DCO is congruent to angle OAB. Well, that's one angle. And notice we got vertical angles there. There's the 2 vertical angles. So we got an angle. Yeah, those 2 triangles are similar. All right, so what did it say if the 2 triangles are similar? It said if 2 triangles are similar, then the ratio of their areas is equal to their scale factor squared. To find their scale factor, I just need 2 corresponding sides. And luckily for us, they gave you the values of the 2 corresponding sides. So one triangle is 3 and the other side is 5 that corresponds with it. So it's just 3/5 squared, right? If I go small to big triangle, you went big to small, it'd be 5/3. And notice, read there in the top in yellow, it says, what's the ratio of the areas of COD, that's the small triangle, to AOB, that's the big triangle. All right, so it's 3/5 squared, in other words, 9/25. Wasn't too challenging. That's the easy one. So here comes the hard one. Same shape, I just made it a little bit smaller here, need some work space. So this time we're doing COD. COD is that top one again, and it's AOD, it's that side one right there. And if you look at them, you might be tempted to say, what's going on here? So maybe draw it off to the side. And if you draw it off to the side, it's pretty instantaneously clear that they share the same height. So those 2 triangles, the green one and the yellow one, as shown right there, they share the same height. All right, so if they share the same height, then the ratio of their areas is the ratio of their bases. And if you look at those 2 triangles, the green one and the yellow one there, the bases aren't labeled. Well, what the heck are we going to do? And boy, is this slick. So most people can get to this step right here, and then they kind of grind to a halt. So let's see what we can do here. Well, we know that for this triangle, we have a value of 3 right here. And then that's it. There's nothing else there between those 2 triangles. But if I go back, I'm going to do this in green now, or maybe I'll do it in blue. So if I go back to this triangle, the bottom one, and the top one, from the previous remarks, we know they're similar. And if they're similar, then that means, well, then their sides are in proportion. And that means all of the sides are in some 3:5 proportion. It may not be exactly 3:5, but it'll be some multiple of 3:5. So if we just look at the blue triangles and we consider, oh gosh, I don't know, if we consider this side right here, this X, and this side right here, this Y, those are the corresponding, because you see that where the arcs are for the angles, those are the 2 corresponding sides. So those two sides must also be in some, I'm going to go backwards and rewrite this. They must also be in some 3 to 5 ratio, except it's going to be a multiple of 3 to 5. And remember, if you don't know what that multiple is, you just put an X. Well, if we go back to now our triangle right here, that means this side is 3x and this side is 5x. And now I have everything I need to solve this problem. I think I do this again. I do it a little neatly with numbers. Definitely similar heights. And the scale factor of the top to bottom triangle is 3 to 5. So that means all the corresponding sides are 3 to 5. Right? Not the triangle on the left there, but top and bottom. And luckily for us, the top one, the bottom one share a certain number of sides with the two red ones that we want. So I can, there it is, nice and neat now. So I can say that side OC is 3x and side AO is 5x. And now I just simply write that proportion. So let's see, if we go to the two triangles, the top one to the left one, that would be 3x to 5x. The x's would cancel out, and it's 3 to 5. Look, I mean, that was pretty convenient. This is a challenging one. All right. One more, I believe. Yeah, one more. So now that you've seen how this is played, the last one is a little bit easier. What's the ratio of the areas of OAB? Where's that? OAB is the bottom one to DAB. Now, careful. I'll show you this. It's not the triangle on the left. It's the whole left triangle. D to A to B. So this whole triangle right there. Should have done that in a different color, but then you wouldn't see the other triangle. All right, so I got a little triangle and I got a really big triangle. All right, so those two clearly do not share heights, but they share bases. The base there is 5, AB. They both share base AB. So let's see, if they share the same bases, then the answer to the ratio of their areas is the ratio of their heights. So I need to find their heights. And I got a problem, but what comes to the rescue is that previous statement. If we look at the top triangle, we're talking about this triangle right here, and the bottom triangle, remember all their sides are in some 3 to 5 ratio. That's their scale factor. And if I look at the two triangles that we have, and I need to find their heights, well, I know this small one right here, and the big one would have, well, this piece right here. That would be its height. If you notice, that would correspond, I'm trying to do a dotted line here, that would correspond with this piece right here. So if we said that the top and the bottom are in a 3 to 5 ratio, and we just attach an X or, whatever, this would be your 3X, that dotted portion, and this would be your 5X. And so therefore this one right here would be 3X plus 5X, it would be 8X. I think I used the letter Y, but it's the same idea. Okay, I think we use the letter Y in the book too, just to differentiate it from the X's. I'll go ahead and just write this out by hand using these values. All right, so let's see the ratio. We got to do the small triangle to the big triangle. So let's see, that would be 5X. We're doing the ratio of their heights over 8X. And the X's would cancel out, and you would just be left with 5 over 8. And that's the ratio of their areas, 5 to 8. There we go. There's 3 problems. Now I'm going to show you this again. I think they use the letter Y, but it's the same idea. Yeah, they use the letter Y. All right. So they have the same bases. So it's 5y over 8y. Remember, where did the 8y come from? 5y plus 3y, so 5 to 8. Okay. Feels like we're done, but we're almost done. All right. So what do we have left? Well, we're going to do a quick summation. Where do we stand? Remember, same heights. It's the area, the ratio of the areas, the ratio of the bases, same bases. The ratio of their areas equal to the ratio of their heights. Similar triangles, scale factor squared. One more thing, we're just going to extend this entire idea more broadly to any similar shape, not just triangles, but any similar shapes. So if the scale factor of two similar figures is a to b, well, then their ratio of their perimeters is going to be a to b, and the ratio of their areas is going to be a squared to b squared. Now, notice I could have written this in fraction form, but it's this basic idea. All right, so that's your theorem. Make sure you write that one down, and we'll do one example. These are actually pretty easy. Now, don't confuse the previous one with this one, although there are similarities, is more general form. This applies to all similar figures. So if you have similar figures that or two shapes that share a same base and they're not similar, we can't use this. All right. However, if they're triangles, you can. So scale factor, and the other one's scale factor squared. So last problem. I got a little Texas, I got a big Texas, and it says, find the ratio of their perimeters and their areas. This is pretty straightforward. So let's see. The perimeter from the previous theorem, it says if you want to find the ratio of their perimeters, it's just the scale factor. Well, the scale factor is, well, it tells us right there, it's 8 to 12. We'd go small Texas to big Texas. So 8 to 12, reduce that. So let's see, 4 goes into both. What, 2/3? Yeah. Lastly, what's the ratio of their areas? Well, we know it's just the scale factor squared. So, well, if we do a squared over b squared, that would be 8 squared over 12 squared. Big numbers, and then reduce. Or, this is the kicker, this is what you're supposed to realize, all you got to do is take that and square it, and you get to that. So a little shortcut step. Now, if all they're asking you to do is find the ratio of the areas, well, then you probably would do exactly that. But if you calculate the ratio of their perimeters, before you do the ratio of their areas, just square the ratio of their perimeters and save yourself some time. Okay, tonight for homework, you're going to have a bunch of problems. There's a table where it asks you to do a bunch of those, and it's much easier just to square the ratio of the perimeters than it is to square their scale factors. All right, believe it or not, that's it for today. So that table is actually not too bad this time. Most of the problems kind of look like this, and if you notice, these are kind of similar to the ones that we just did there in class. All right, and the table, and once again, there's the table. And remember, the scale factor is the ratio of their perimeters, and you simply just need to square that to get to the ratio of the areas. So maybe this table is just a bit too easy for today. Maybe not, you'll see. But that's it for today. If you have any questions, make sure you ask. If not, I can't remember if this is the last class of the weekend. If it is, have a great weekend, and I'll see you again.